Just to explain the idea of DEM differencing, what we have here on the left are two DEMs that were derived from surveys at 2 points in time. We've got a new DM and an old DM, and all a DEM of difference is when we simply take, and on a cell-by-cell basis, if this is a blown-up view of each of those DEMs, on each overlapping cell, we simply subtract the old DEM from the new DEM to get a DEM of difference. And if we do it in that order, positive values should correlate to deposition, shown here in blue in both of these figures, and negative values in red should correspond to erosion. And so what we have then is a spatial map of erosion and deposition. Another way of looking at this is just with a simple distribution of the DEM of difference. So we'll call this an elevation change distribution. And if we take a closer look at that elevation change distribution, it's really just a histogram of elevation changes, which is what the DEM of difference calculates. And in the middle here we've got 0 or no change, and then everything to the left would be erosion. The negative values, everything to the right would be positive values, we'd call deposition. And so this is one of the things that the geomorphic change detection software produces, is these little outputs. And it does two types of histograms. One is a surface area distribution, which is the same as really a count. And so this is, the total area of erosional cells in each of these different bins of elevation change versus depositional cells. And then if we look on the bottom here, instead of area on the vertical axis, we've got volume on the vertical axis. And so you notice that the shape changes, and the reason for that is because each of these little bins is then multiplied by the magnitude of elevation change. So closer to the middle here, towards no change, we're talking about multiplying by small values, and so it has the effect of sort of retarding the distribution in the middle, and then towards the periphery, it amplifies the magnitude of the elevation change distribution because it's multiplying it by larger numbers. And so both of those turn out to be really helpful ways to explain your DEM of difference and visualize it. Just to back up for a second here, we've got these DEMs of difference that we can calculate with this simple sort of raster operation where we're just subtracting the two surfaces from each other. And this is helpful in terms of sediment budgeting. If we want to try and do a sediment budget for a reach, it's basically a statement of conservation of mass. We want to look at how much volume of sediment, say, is coming into a reach at the top here, how much volume of sediment is leaving the reach, and then how much change, which is this term here, the change over the same time period, took place in this. And so what a DEM of difference does is it only solves for one of those terms in a sediment budget, or this conservation of mass. And when people refer to closing the sediment budget, they're trying to take measurements of these fluxes, integrate them through time, and then hope that they match up with the measurements in the change in storage volume. One last thing that's worth considering when you're looking at these elevation change distributions, and is really our motivation for making the geomorphic change detection software, is when you look at a lot of distributions, you'll find that there's a huge peak centered around 0. And it's fair to ask, is that real? Is there any basis for having a whole lot more small changes than you would have real changes? And then, to answer that, we can consider, well, what really needs to happen for me to calculate that there's absolutely no change, that there's 0 change? Well, it means that I have to go and I have to survey an area, and I would have to survey the exact same elevations 2 times in a row. And just given the precision of our survey equipment, the odds of that happening are very, very low, and they're made even lower because we then take that survey data and then we interpolate it into a surface, typically a tin, which then gets to work in this software anyway, converted into a raster or gridded DEM. And so the likelihood of that actually happening and actually having absolutely no change is very, very small. And so what happens is that you have very, very small changes, a whole bunch of them, and we don't know if those changes are real or if those changes are just noise related to the imprecision in our ability to do repeat surveys as well as interpolate surfaces. And so that is the motivation for looking at the uncertainty in these individual surfaces and seeing how it propagates into the DEM of difference.